All right, so this is the topic 2 video for lesson 4, and we are going to jump right into an example that I'm actually taking from your calculus book. So if you happen to have it in front of you, it is on page 126, and it's called example 4 in your book. So I will read it as it is in the book, and then I have a little summary for us on one of our extra pages here so that you'll be able to take those notes down. So let me read it first. Okay, page 126, example 4. It says, a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, which is approximately 109 miles per hour if you wanted to know. That has nothing to do with anything else we do, but 109 miles per hour, that's pretty fast. It reaches a height of, and it gives us an equation for position. So it's going to be S equals, for position, S equals 160 t, t is for time, minus 16 t squared, and that gives us the answer in feet after t seconds. So I know that's hard to capture all that in your head without seeing it if you don't already have your book in front of you, but here's my little summary. As you'll see, there's this fun little explosion happening kind of right over my head, and there is a rock that is being propelled upward at approximately 109 miles per hour, or more specifically, the velocity is, or the initial velocity here is 160 feet per second. At the top, above that little squiggly cloud looking rock, you'll see the equation that they've given us for position, which remember is in feet based on time in seconds. So S's position equals 160t minus 16t squared, and that's in feet. All right, we need to answer 4 different questions. I'll read the exact wording here, but I've kind of summarized it for you in pink. So our first question is going to be, how high does the rock go? Secondly, what is the velocity and the speed of the rock when it is at 256 feet above the ground? And that's going to be on the way up and on the way down, right? Because it's going to, if we're blasting the rock upward, then it's going to hit all those positions, reach whatever the climax of its height is going to be, and then fall back down through all those positions to the ground again. Letter C, the third question will be, what is the acceleration of the rock at any time t during its flight after the blast? And then lastly, when does the rock hit the ground? Okay, those are our 4 questions, and as always in calculus or physics, we're going to look at each one at a time. But before we even answer these questions, or A, because we're going to start with the first one, I would recommend that anytime you have a question like this, we create our little, where's my green? Our ladder of, sorry, I'm drawing crooked again. That's going to just bother me. Watch, I'm going to probably do it again. Ready? Oh, that's good. That's nice and straight. Okay. Oh, that's not. I'm sorry. Okay, we're going to have 3 sections of this ladder that we're looking at. One is going to be for our position equation. Then we're going to use that to figure out our velocity equation and our acceleration equation. Usually we don't need to worry about jerk. It doesn't happen really with projectile motion. We don't end up with jerk because it's moving upward and downwards with an acceleration due to gravity, not due to like accelerating or decelerating a car. So we're going to leave jerk out of the equation. We don't need that equation. Okay, so S we know, V we don't know, and A we don't know. So as the obvious starting point is, let's start with S. So going back to our question, we see that the equation for S is 160t minus 16t squared. And we're just going to copy that right here. 160t minus 16t squared. Okay, so we want to use that information to find the subsequent ones. And if you remember from the first video, that's actually pretty easy for us to do because the relationship between each of these functions is they are the derivative of one another. The velocity is the first derivative and the acceleration is the second derivative. So let's use what we know about derivatives to change the position equation. So the derivative of two objects that are being subtracted, we can derive them separately. So the derivative of 160t is just 160. So we've done that several times now. That's really a power equation, right? Because we have a power of 1. We're bringing the 1 to the front and then dropping that power to 0. So the derivative of the first term is 160. The derivative of the second term, we're going to take that 2, swing it to the front, and drop the power down to a 1. So that's going to give us 2 times 16, so that's 32, t to the first power, or just t. So we have velocity equals 160 minus 32t, and that's it. That is the velocity equation. We didn't have to memorize a separate equation. We didn't need the problem to give us that information. We just can figure it out using mathematics because velocity is just the change, the rate of change of position. Let's do the same thing to find acceleration because we derive to get the first equation and then we derive again to get our acceleration equation. What's the derivative of a constant? Well, the derivative of a constant, it doesn't matter if it's 160 or 1 million or 1, it's always 0. So I could write 0 or I could just leave it off, right? Because it's not important. So that derivative of that first part, it causes that term to go away. Then let's look at negative 32t. Again, that's negative 32t to the 1 to the first power. So that 1's going to swing to the front. It's not going to change anything. It's going to drop down to a power of 0. So what we end up with is just negative 32. And it's just that. It's just a number, right? So we have our position equation, our velocity equation, and our acceleration equation. Now, if you're wondering, what does it mean that acceleration is just a number? Does it matter that it's not a function? Well, remember that we said right now the only accelerator in our physics problem is gravity. And gravity doesn't change unless you change planets, like totally have to uproot yourself from planet Earth and go somewhere else in order for our acceleration due to gravity to change. So this would be actually negative 32 feet per second squared, which is actually acceleration due to gravity using feet. And this, the top equation was, of course, in feet. That makes the second one in feet per second. And of course, it is really important to have the correct notation or the correct units here. Okay, we haven't necessarily answered A, B, C, or D, but we've now done most of the math work that we're going to need, at least to have our working equations. Okay, so let's leave them there. I'm not going to erase them. I've actually created 3 different screens for us. Yeah, that's the word I want. 3 different screens so that we can keep the information and not have to erase it until we move to the next point. So going back here to our question A, how high does the rock get? Well, looking at our 3 equations, position, velocity, acceleration, if we're talking about how high, we are talking about a type of position. So we're going to want to use this top equation. The problem is, in order for us to figure out how high the function goes, we would need to know when, like what time, at what time are we reaching the highest point. And our position equation, honestly, doesn't give us any of that information. And even if we go back to our problem, it doesn't tell us how long it takes to get to the highest point. So our first thought is probably, we need more information. But the information we're looking for is actually embedded within one of the equations. Specifically, let's look at velocity. So the velocity equation is just 160 minus 32t. You might be thinking, what does this have to do with the highest point? Well, directly, it doesn't necessarily have anything to do with the highest point, but something special happens at the very top of when you have projectile motion. Something is being thrown upward into the air, and then it turns around and falls back to the ground. At that highest point, the special thing that happens is that the velocity becomes 0. So as we're moving upward, we can call that all positive velocity, moving upward into the air. And then as it moves downward, it's all going to be negative velocity. But for that infinitesimally small point in time, at the highest point, at the climax of its motion, the velocity for that moment in time is 0. So, if I took my equation that I have here for velocity and I plug in 0 for v, I end up with an equation that only now has one variable. That variable is t for time. It's solvable. So if I go ahead and isolate t, I will know the exact time when the velocity is 0, which is also the exact time when we're at the highest point of this motion. So let's figure it out. First, I'd subtract 160, so I'd end up with 160 equals negative 32t. Oh, actually, you know what? I'm not going to do it that way because I want to show you something here that's kind of important. I'm actually going to show it to you using factoring, and there is a good reason why I want to do that. Just in case there was ever actually, you know what? I don't need to do that. I'm sorry. I'm like thinking of the next problem. Just pretend I didn't say that. I don't want to start the video all over again. So I'm thinking about this as we go. Scratch that thought about factoring. I'm going to do that somewhere else on this problem. So hint, hint. Okay, we will go back to it. I'm going to subtract 160 equals negative 32t. And then we would want to divide both sides by negative 32. So let's pull out our handy dandy calculators, unless you have 160 divided by 32 memorized. And we get 5. I knew they were going to give us a nice number. I should have guessed it was 5. I should have been able to see that. That's all right. 5. And what does that mean? Of course, because we don't want to just say 5. It means 5 seconds. So in the context of our little explosion throwing a rock into the air, what we now know is that it took exactly 5 seconds for it to get from its initial starting point, its initial position, to its highest point before it started to fall back down again. Now, if you go back and look at the first question, we still haven't figured out what the answer is. We figured out the time. We know that it happens at time equals 5 seconds. But that isn't actually what they're asking us. They're asking us, what is the position? How high does it actually get? And in order to solve that, we do need to go back to the position equation. But now we're going to have the information we need, because here's our position equation. It requires that we plug in a value for t, and we now know that that value is 5. So with a quick, I'm actually going to just say, I don't really need to rewrite this, 160 times 5, and then it'll be minus 16 times 5 squared. So we're going to, again, plug this into our calculator, and we'll get 160 times 5 minus 16 times 25, really, right? 5 squared. And the answer is 400. So what does that mean? This is a position equation. It gives us units of feet. 400 feet is now the answer to our first question. How high does it go? Well, 5 seconds to get there, but 400 feet is the height once it reaches that point. All right, that was question 1. What about question 2, which doesn't ask us about position, it asks us about velocity and speed, and we're seeing this purposeful mentioning of velocity and speed alongside each other so that we can remember velocity is allowed to be positive or negative. Speed is always positive, so we have to be careful when we give those answers. Okay, so the question is, are you ready? You can take a deep breath. You can pause and clear your head if you need to. Okay, ready? B. What is velocity and speed at 256 feet on the way up and on the way down? So what is the velocity and speed at 256 feet? So we're going to have to do this problem kind of the opposite of the last one. We want to find out speed, but all they're giving us is information about the position. So we're going to have to use position to find time, and then use time to find velocity. And you're going to find that this happens a lot. Time is the one variable that connects everything. So you have to take the information they give you and usually use it to find time, and then time unlocks your ability to find anything else that you need to know. So right now they're giving us information about position, 256 feet, and we're going to use our position equation to find the time of that. So 256 feet, we want to know what, we're plugging this in for S, right? So that's 160t minus 16t squared. Okay, here, this is what I was thinking of in the last problem, where I thought I was going to factor in. I wasn't going to factor, but I am going to factor now, because what we have here is really a quadratic equation. And the way we solve quadratic equations is either we factor or we use the quadratic formula. And we really can do either, but this one happens to have a nice, like easy factoring to it. So I'm actually going to move everything over to the left side because we want it all to equal 0. So I'm going to get 16t squared, then it'll be minus 160t plus 256 equals 0. So all I've done is just take those terms on the right and move them to the left. We can see that each one of these terms is divisible by 16, and that's what makes this easy to factor, because I can pull that 16 to the front. I get t squared minus 10t plus 16 equals 0, just by dividing the 16 out. Is that factorable? Yes. You can kind of ignore the 16 because it's not going to change our answer right now, but it would be 16 on the outside. And then we'd have t minus 8 times t minus 2 equals 0. Now, if you're trying to, I don't know how freshly all that, well, hopefully at this point we're feeling like all the math juices are really going, but remember we need the two numbers here to add to negative 10. So we have negative 8 and negative 2. That makes negative 10. And we need them to multiply to 16. So we have t minus 8 times t minus 2. How do we solve this? Well, we're asking what value of t would make this whole equation 0. And there are two answers. Either if t was equal to 8, so t equals 8 seconds, by the way, because remember we're talking about time, or when t equals 2. Now let's think, does that make sense that there are two intervals of time when our rock is at 256 feet? And I think you would agree, yes. In fact, we expected it. Two seconds into it, it's still traveling up, because remember at 5 seconds we decided that that's when it hits the highest point. So at 2 seconds, we're still moving up. At 8 seconds, it's on its way back down. So those are the two instances. Now remember, we're not really looking for the time, which right now is 8 or 2 seconds. What we're really looking for is what was the velocity, and then also, likewise, what was the speed at those 2 points in time. That is not information we're going to get from the position equation. We figured out the time, but we're not going to get the velocity information here. We need to clear this out, and we need to use our second equation, velocity, 160 minus 32t. So let's write that out. So velocity is 160 minus 32t. And we know that we're trying to find out information about t equals 2 seconds and t equals 8 seconds. And if we go ahead and plug this in, 160 minus 32 times 2, we're going, I'm going to kind of cheat here and just look at the answer I have in my book. You probably have it right there too. So it is going to give us a total, I think it was 96. Does it give us 96 feet? See, I probably could have figured out faster with my calculator. Yes, it does. Okay, so if we plug in 160 minus 32 times 2, we get 96 feet per second. If, on the other hand, I plug in 8, I'm actually going to have more negative than positive, and so my answer is going to be negative 96 feet per second. But that should make sense to us, right? It's moving, it has a positive velocity on the way up and a negative velocity on the way down. So that is the answer. At 2 seconds, it's 96 feet per second. At 8 seconds, it's negative 96 feet per second. How does that change if I ask for speed? Well, we would say speed is 96 feet per second at both points. So we just make it positive because remember, speed is really, think of it like a speedometer. A speedometer on your car does not have negative numbers. It's all positive because it's just telling you how fast you're going. So that's what we're asking for here. That's the difference between velocity and speed. I don't know, do I actually have, well, I'll just put the 96 feet per second here because I really don't have much room to add it in. But you can put it in your notes as however you want to write that down. The answer would be 96 feet per second at 2 seconds and negative 96 feet per second at 8 seconds. Okay. That's check for first question, check for the second question. The third question, you can take a nice deep sigh of relief because we've actually already solved this one. It says, what is acceleration at any point in time? And when we made our little ladder of functions, of derivatives, we figured it out already. We found out that the acceleration is always negative 32 feet per second squared. And again, we said that makes sense to us because that is the acceleration due to gravity. So we already figured that answer out. And then lastly, it's going to ask us, when does it actually hit the ground? And it's going to take as much time to get from, or maybe let me phrase it a different way. I think without having to do really any math here, if you think about the motion of something going up in the air, oh, I want to do a darker color. So we have an object, it's going up in the air, it hits its highest point, and then it falls back down. It's going to take the same amount of time to get to the highest point that it's going to take to get back down to the lowest point, as long as we're neglecting wind resistance and those kind of variables, kind of messing with things. But in this ideal situation, it's going to take the same amount of time to go up as it is going to take to come down. We already figured out how long it takes for us to get to the top. In fact, it said we found out it took 5 seconds to get to the highest point. So if we want to know how long it takes to get from initial to final position, the answer is just double this value. We don't have to do any extra math. So the answer is 10 seconds to make that whole trip up and back down to the ground. So 10 seconds is that last solution. So we did C, we did D, and we are done. Now, I'm going to say that whenever we're doing a physics problem, you're probably going to need to know information about position, velocity, and acceleration. So you might as well just create that little ladder that we had right away. Like, don't wait, because then you're going to be trying to figure out what information you do and don't know. Just create that little ladder of derivatives and you'll get yourself ahead of the game. And then secondly, remember that in a problem with multiple steps, take one step at a time. Don't try to figure them all out at once. I know it can be overwhelming. Sometimes I think we have this like anxiety reaction that makes us want to figure out the last problem as fast as we can figure out the first problem. Just block out the other 3 parts of the question and look at the first one. And then block out the last 2 and look at the second one. And that's how you make it through these larger problems. And we are going to have a lot of them. Calculus introduces a lot of interesting, deep, multi-layered problems. And so you need to develop that that skill of blocking out the part that's not important until you get there. All right, that is it for topic 2 for this example problem. And now topic 3, I know we have more video content than we normally do, but I want you to have these examples written down in your notebook so we have some foundation laid before we get started in class. So this last one is a short example, a very short example of how derivatives are also seen in economics. So it's much less complex. In fact, most of it is just what we call plug and chug in mathematics. So you have a function or a formula and you plug information in. But I do want you to see the connection in economics for derivatives. All right, so you're almost there.